All right, so our notes today, we only have two problems. There's only two problems we're going through today. It's optimization. It's a little bit strange, okay? And so bell work here is really a third question. This is really going to do exactly what we're doing today in bell or in our notes. So don't be perplexed if this bell work looked a little hard, because it is, okay? It says the marketing department at Texas Instruments has found that when certain calculators are sold at a price P, okay, so price is P, the number of calculators sold, X, is given by this demand equation. So the amount of calculators bought is equal to that, 2100 minus 150, 21,000 minus 150p. Using the revenue equation, R equals XP. And so they tell us this equation, and sometimes students get perplexed by that. I keep using that word a lot today. I apologize. Perplexed is not a word I should be using quite so much, but I am. Revenue equals X times P. Revenue, how much money you make, is equal to the amount of things you sell times how much they are. It's not as hard as it is. All right. It's just a pretty straightforward equation. Find a model that expresses the revenue R as a function of the price P. So we are going to make revenue in terms of just the price P. So right now, revenue has two variables. It's got X and P. I want it to just be P. What could I do with this equation to make it just P and not X and P? Lydia? Yeah. Substitute what X is. Right here it says X is equal to this thing right there. That's what X is. And so if revenue is equal to X times P, all I have to do is substitute in for X. I'm going to take my X equation right there and plug it in. All right, so instead we're going to write our new revenue equation, which is going to be this. 2100 minus 150p times P. I took this, I plugged it in right there for X. That was step one. I wrote a revenue equation just in terms of P. Step two says, what is the implied domain of R? The implied domain, a little bit strange. It's a parabola, okay? Because if I distributed in that P, it would be 150p squared. That's a parabola. What is the domain of a parabola? All real numbers. That's not what the question's asking. It's the implied domain. All right. When you're thinking revenue, what would be bad with revenue? Negative would be bad. You do not want to lose money. That would be a bad thing. So in other words, understand what they're saying here. All right. We've got this equation. This is revenue. I know it's going down. Okay. Like if I were to distribute this in here, it would be negative 150p squared plus 2100p. It's a parabola. It's going down. It's going to look like this. It's got two spots right there. The implied domain means basically when is the revenue positive? That's what we want to find here. So we're looking for the X-intercepts as we set this thing up. It's already factored, so it's easy. I'm taking each part and setting it equal to 0. Okay, taking each part, setting it equal to 0, so P is equal to 0. So yeah, it's 0 right there. And then I'm going to solve this one. So 2100 equals 150p. I just added that 150p over. And then divide by 150. 2100 divided by 150. My p is going to be 140. Somebody do that already? Great. I'm going to assume that it's 140 then. It's 140. That is the implied domain. The implied domain here is 0 to 140. Remember, my X value here is P. The P is what's being graphed down here. So this is the price down here. So what that means is if I sell the calculator between $0 and $140, I'm going to make money. Okay. If I sell for more than 140, it becomes a non-realistic equation. Question number 3 says, what unit price should be used to maximize revenue? Remember, this is a graph. This is revenue equals. This is a graph of revenue. I want to know what unit price should be used to maximize revenue. Where is the maximum of revenue going to occur? The vertex right up there. That's the vertex. That's when the revenue is going to be at a maximum. How can I find where that's going to happen? You could put it in vertex form. We could do that. You could complete the square. I don't really want to do that. I don't want to have to factor out 150. We could probably, but what else could I do? Yeah, let's do that. Let's go negative b over 2a. That's going to find me where the maximum occurs. All right, so negative b over 2a. So I'm looking at this form right here when I've already multiplied it out. That would be handy. So I'm going negative b. So negative 2100 divided by 2 times negative 150. I'm going to type that in. Negative 2100 divided by 2 times negative 150. I get 70. What does that 70 represent here? That's the price. That's how much money it is. Okay? That's the price right here. This is happening at $70. If we would have found that, we probably could have gotten the implied domain that if 70 is in the middle, we could probably go halfway each way and figure out there. But that's 70 bucks. That's the implied price that's going to maximize our revenue. If this price is charged, what is the maximum revenue? Not where is the maximum revenue or what price should it be. It's what is the revenue. What am I going to do to find the revenue now? Plug it into what? Right there. Revenue equation with P in it. Okay, so I'm making revenue. And I'm going to plug in 70. It's going to be negative 150 times 70 squared plus 2100 or 21,000. P. And for P, I'm plugging in 70. I take that whole thing. I type it into my calculator. I hit enter. My revenue is going to be equal to $735,000. So in other words, if I sell that calculator at 70 bucks a piece, I'm looking to make $735,000 during that time interval. The last one says how many units are going to be sold at that price. Which equation am I going to plug into to figure out how many units are going to be sold? You could do X equals this equation right here. X equals right there, 2100 minus or 21,000 minus 150p. You could do that. What other equation could I plug into? That one right there. We know what the revenue is. It's 735,000. This guy right there, 735,000. It's going to be equal to X times my P. So in my calculator, I'm taking 735,000 divided by 70. My X is going to be 10,500. You can plug into either one. That one makes a little more sense because it's an easier equation, but you get to pick. Once you find your information, you should be good. That's exactly what we're doing today. So if you can follow along with me there, we're going to do that same process the rest of the day. Okay? It is called maximizing or optimizing an equation. Here we go. So wrong page. Today, we are talking about optimization, okay? Again, one of the trickier lessons that we're going to work through, but it's not really. Once you figure it out, it's easy. It's just a matter of getting your brain wrapped around what's going on. So what we're trying to do today is build quadratic models from verbal descriptions. So we're going to give you a situation. You're going to try to write a quadratic based off of it, and then eventually we are going to optimize it. Okay, this is a business thing all the time. When you run a business, you want to make as much money as possible. You want to try to make it fire on all cylinders and get everything you can. That's what optimization does. Okay, this is a very real world problem that I guarantee that every business that's successful is doing all the time, trying to optimize what they got. All right, so for some reason, farmers love this. You're going to see this all of the time with a farm field and some fencing. Just get used to it. Right now, you guys don't know quite enough to get crazy fancy. When you get into calculus next year, we'll do some more optimization problems. But for right now, be ready for those pigs. Here we go. A rancher has 400 feet of fencing with which to enclose 2 adjacent rectangular corrals as shown. What dimensions should be used so that the area or the enclosed area will be a maximum? What is the maximum area? All right, so they drew this thing for you. you've got this corral. You've got an X and a Y there and a Y in the middle. You're making two separate corrals. You got a pig corral and a cow corral because if they get together, they just get a little too wild. And then we put the X's there. We good? What are we trying to maximize? That's the first thing we're looking at. As we read these questions today, we're thinking, all right, what are we trying to optimize? The enclosed area. The area needs to be at a maximum. So we are trying to maximize area. Write an equation with your neighbor. What is the area going to look like for this thing right here? We are trying to find the area of the pins. Anybody got an idea here? What could our area be? We want to find the area of the whole thing. I'm glad we're all saying it here. 2x, y. It's a rectangular pin. Okay? If you did one of these squares, it'd be x times y. If you did the other one, it'd be xy. So my area is going to be 2xy. Okay? Or you could look at the whole length. This is 2x. This is y. We multiply it together, it gets 2xy. Okay? That's going to get me area. Great. Notice that my equation right now, my area equation that I'm trying to maximize has two variables. I've got x and y. All right. We can't solve an equation like that with an x and a y in it. There's too much stuff going on. We need to rewrite that somehow. And the way we can do that is by utilizing a limiting factor. There has to be something else going on here. Otherwise, I'm going to make the world's largest corral. It's going to cover the entire face of the earth, and my cows will be really happy. All right. Something has to limit here, and there is something. So we're looking for a limiting equation. Okay, something has to be limiting us in some capacity. For this problem, what is our limit? What is the thing that we have to maintain? 400 feet of fencing. That's all we got. Technically, you could be less than or equal to. We're just going to say equal to 400 feet. All right, so we need to now write an equation that talks about our limiting factor. So we have 400 feet, write an equation for the fencing that we're going to use. Jack, what do you say here? 400 is going to be equal to what? 4x plus 3y. Good. A lot of people say 2y. Don't forget about the one in the middle. So we've got an x, an x, an x, an x. So 4 x's, that's the fencing. And then there are 3 y's because there's got to be one in the middle as well. So when I add all of those pieces of fence together, it has to be equal to 400. Everybody good there? Once we've set this up, we are trying to now take this equation and substitute in there. Just like we did in Bellwork, with a revenue equals XP equation, we substituted in so we had one variable. Same thing's happening here. Which equation do you want to solve for, X or Y? It doesn't matter. Let's pick X since nobody had a suggestion. Let's solve for X. It doesn't matter which one we pick. Let's do X. All right, so I'm going to get X by itself. So I'm going to subtract 3Y. I'm going to divide by 4. So I get 100 minus 3/4 y is equal to x. It's the same equation. We just made it into x equals. Once I've done that, once I've found my new limiting equation in terms of one variable, we are going to take that and we are going to substitute it back in to our maximizing equation. So we're taking our limiting factor and plugging it back into our maximizing equation. So now we get this. Area is going to be equal to 2 times 100 minus 3/4 p. I'm sorry, 3/4 y times y. I just substituted what x is equal to in there and we multiplied it in. Then I'm going to go ahead and just clean this up because right now this is super ugly. So I'm going to distribute the 2 and the y in. It's a little bit funky, but we can do that. So it's going to be A equals 200y minus 2 times 3/4. Okay, that's minus 3/2 y squared. Or if you would like, negative 3/2 y squared plus 200y. We took our equation, we rewrote it. Now it's in a form I can handle. I've got an area equation that is written with one variable. That's what we want. We don't want multiple variables. I got one variable. What shape is that equation going to look like? A parabola. Which way is that parabola going to open? Down. It is a downward facing parabola because it's y squared and it's negative. We are trying to maximize the area. Where is the maximum area going to occur? At the vertex. So if I find the vertex, it's going to answer my question. So all we need to do is find the vertex. So to do that, we are doing negative b over 2a. You could complete the square. You don't want to do that. It's going to take a little bit too much brain power. Instead, let's just do this. Negative b over 2a. So negative b, so negative 200 divided by 2 times my a. I'm going to break out my calculator and figure out what that is. These 2's kind of cancel. The negatives kind of cancel. 200 divided by 3. How many decimals should I go to? 3 decimals always in here. Okay, some of you already forgot that on our first test. 3 decimals. 66.667 is what you should have got. That is the y dimension of my corral. That's what my y is equal to. Okay, it seems a little weird there, like, oh, that was my x. But again, remember this equation was written in terms of y, so that's solved for y. Great, there's my y. Find your x. Now that you found your y, found your x, talk with your neighbor, get that figured out. All we're doing here is substituting. If I find my y, I can plug into any equation. That equation right there would be nice. 100 minus 3/4 times that. My x is going to be equal to 50. My x is 50. So the question was, what dimensions should be used in the enclosed area will be a maximum? Here it is. My y should be this. My x should be that. That's sufficient for dimensions. The last question is, what is the maximum area? How do I figure out what the maximum area is going to be? Plug it into which one? The area one. You got 2 of them. You get to pick which one. You could plug in right here if you want to. Oh, that's the worst color combination I've ever seen. You could plug into that equation right there if you wanted to. But it's just as easy to plug into that one. Okay, that 2xy equation, all we got to do to find our area is going to be 2 times x times y. We type it in, we hit enter. The answer is 6,666.667 feet squared. Whole lot of 6's there, but we're all right. Questions on something we did? Again, think about what we did. I'm going to talk through my steps. We found a maximizing area. Okay, what equation are we trying to maximize? So we did this first. Once we did that, we wrote our limiting equation. So what thing limits us? We got it in terms of a variable and substituted in. Then we took our parabola and we found the maximum using our vertex. Those are the steps, exactly like the 4 steps we did in Bell. Let's try it again. So the first one is going to be the one you see the most of. The next one, a little bit different, but we can handle it. It says a track and field area is in the shape of a rectangle with semicircles at each end. The inside perimeter of the track is 1,500 meters. What should the dimensions of the rectangle be so that the area of the rectangle is a maximum? Let's label this the same so we don't get confused. Let's talk about this right here, this distance. Let's call that x. And then let's call this distance right here y. Just so we're all on the same page. With your neighbor, write an equation for what you were trying to maximize. What are we trying to maximize again? Area. And so area specifically of the rectangle. So my maximize the area, what equation is that going to look like? XY. That's the easiest one. x, y is my equation. Because it's just the rectangular part, x times y, length times width. We're good there. Once we find that, we're going to find our limiting factor. Something has to limit us. Otherwise, we're making the world's most giant track and field event. Okay? So, what thing here is limiting us? The inside perimeter needs to be 1,500 meters. The inside perimeter, all the way in the track, needs to be 1,500 meters. Take a second with your neighbor and write an equation for that. Yeah, when we talk about inside perimeter, that is this whole inside loop here. All right, we're trying to find the inside perimeter, so we need to write an equation with that. Anyone confident in their equation? Jack, what you got for us? Pi times y plus 2x. I'm definitely good with the 2x part. We got the red line and the red line. That's 2x. Where are you getting pi y from? Yeah, what's the equation for the circumference of a circle? Yeah. So circumference is pi d. Sometimes students will say 2 pi r, but 2 times the radius is the same thing as the diameter. So he's got two semicircles here. When he puts them together, their circumference is going to be, the diameter is going to be y. So pi times y is going to get me the circumference. Wonderful. There's my limiting factor. Once I've got that limiting factor, I then need to get that by one letter so I can substitute it in. What letter do you want to solve for? X. It doesn't matter. You can pick. If you said y, solve for y. I'm going to solve for x. That way we're all on the same page. But it doesn't truly matter. You can do whatever you want. Okay, somebody said x louder, so I'm going to go with that. 1,500 minus pi y equals 2x. I'm getting x by itself, so I'm going to divide by 2. That's going to cancel. 1,500 divided by 2 is 750. And then that's like pi over 2y is equal to x. Okay, so we've got x is equal to this equation. Once we've got this equation, we got x by itself. What am I going to do with that new thing there? Plug it in. I'm taking it and I'm substituting it in for x. So now I can write this equation. Area is equal to 750 minus pi over 2y times y, because I got that y right there. I'm going to go ahead and distribute that y to everything just so I have it and make it a little bit cleaner. So my area is going to be equal to negative pi over 2 y squared plus 750y. Finish that question. Talk with your neighbor. Finish that question. We're finding the maximum. So if you're finding the maximum, you're finding the vertex. Negative b over 2a. So it's negative 750 divided by 2 times negative pi over 2. Negative b over 2a. I'm simplifying this. I got a 2 here and a 2 there. That could cancel. So really it's just 750 divided by pi. We're not in 5th grade anymore. Make sure you're using the pi button. Okay, don't use 3.14. That's not going to cut it. Divided by second, and the little upward arrow right there gets you the pi button. Make sure you're using that. 750 divided by pi. How many decimals should I go to? 238.732. So my y value equals 238.732. That's the y value, meters. Then I want to find the x value, meters. How do I find the x? Plug it in. Pick which equation. I'm going to go right here into that 750 minus pi over 2y. So 750 minus pi over 2. It took me forever. I feel like it was like 2 years ago that I learned this. So I'm going to teach it to you, even though you probably already know. 750 minus pi over 2 y. If I want to use y, the answer I got in the last one hit the up arrow on your calculator and highlight the answer that you got, and then hit enter, and then it will use that answer. I didn't know that. I always used the answer button. It works that way. Way easier, though. 375 is going to be my X value that I'm looking for there. What should the dimensions of the rectangle be? That's what the dimensions of the rectangle should be. 238.732 for your Y and 375 for your X. It's a big track, by the way. There's not any tracks that look like that, but we can handle it anyways. If you wanted to find the maximum area, what would you do to find the maximum area? Yeah, multiply them together. It's X times Y. So this thing times that thing. That is what the maximum area should be. They didn't ask for that, but there's the answer. 89,000 square meters. That's a large area. All right, here's what I want you to do with your neighbor real quick. Sum up. When we talk about an optimization problem like we're doing, come up with like 4 steps. What are the 4 main steps that we had to do in order to solve that problem? Let's see. These aren't always going to be area problems. Sometimes we do revenue, okay? Sometimes we might do something else, but we're going to see a lot of area. It's just going to happen. It's just what right now the skills that we have for it. When we're doing these optimization problems, Kara, what did you guys say the first step was with these equations? Yeah, find your maximize equation. Technically, it could be a minimize equation as well. That's why it's called optimization. Sometimes you might minimize, but find that maximizing equation, okay? Whatever it is, what are you trying to maximize or minimize? We need to find that first. Once we found that, okay, then we're going to work from there. Megan Copeland, what did you guys say next? What's the next step? Find our limiting equation. There has to be something limiting us. Otherwise, we are going to just not have any bounds, and we can't solve it. There has to be something that's limiting us in what we're doing. Matthew, what next? Get it solved for a variable. And I'm going to say and substitute as one step there. Solve for variable and substitute. We have to have our maximizing equation in terms of one variable. And so just like this equation right here, we got x by itself, and then we had to plug it into our original equation. And then once we've substituted in step 4, what should our last step be? Yeah. Find the maximum. Solve the parabola. I don't know if that's a great step, but that's what we're trying to do. Okay. We're trying to find the maximum or the minimum in that problem and just answer the questions. Okay. Find the maximum, find the minimum, answer that question. That's the ultimate goal. Show me with your fingers on a scale of 0 to 5, 0 meaning you knew any of it.